Hi guys. So today we are going to look at logarithms. Now a lot of you actually have already talked about these before because you've seen them. Logs are actually just another way of writing exponents. Okay, it's very similar to an exponent, kind of just the inverse operation. The reason we need logs is to evaluate some of these types of questions. So 2 to the x is equal to 4. We can figure out that x is equal to 2. Okay, because we know 2 squared is 4. Same thing on the second one. I know that 2 to the third power would give me 8. Okay. The problem is when I get to something like this, 2 to the x is equal to 6. I don't know what power I need to raise it to. So we use logarithms to be able to evaluate what that exponent is. So again, a log is the inverse of an exponent. So if this is your log expression, this is the equivalent exponential expression. Right? A couple things that need to be true. It says y is greater than 0. That's this part. Okay, that's called the argument. The argument has to be positive of a log. Okay, and then the base, so the base of the log is the little number. The base of an exponential function we've already talked about. Okay, so they're both bases. It's the same value. That's what makes these a little bit easier to rewrite. That base has to be greater than 0, but that base also cannot be 1, because if that base is 1, it's not going to be a log. It's just going to be a constant number. So let's rewrite a couple of these. Okay, I think the easiest thing to do is you start at the base and you go in a circle. So 6 to the third would equal 216. Again, start at the base, so 7 to the 0 is equal to 1. All right, 21 to the first is equal to 21. And again, it's the base is the bottom 21. And then same thing here, 1/5 to the -1 is equal to 5. And we know that's true because a negative exponent would flip that fraction and give us 5. Okay, now rewriting it the opposite way. This is going to be really important for solving exponential equations. So again, the base becomes the base. So this becomes log base 9. So the little number is the base. It's the same as the exponential base. All right, and then again, we go in a circle. So the next number would be 81 is equal to 2. Okay, the exponent is on the side that's by itself. The exponent is on the side that's by itself. So right here, log base 20.05 is equal to -1. All right. Log base 16 of 8 is equal to 3/4. Again, start at the base and then go around. Start at the base and then go around. So log base 15 of 1/225 is equal to -2. So if you feel pretty comfortable, pause the video and try to rewrite this expression for us. All right, so this would be log base 2 of 6 is equal to x. And if we were to actually evaluate it, this is what we would plug into our calculator. Okay. The only thing with these is just be careful in case they rewrite it the opposite way. So let's say it was 6 equals 2 to the x. Okay, I would still start at the base, but when you go around, you're going to need to go away from that exponent. So it would be 2 log base 2 of 6. That part can get a little tricky sometimes. So what I usually do is I like to always put the number, if it's on the opposite side, I would just rewrite it on the other side to make it a little easier to follow that circle. Okay. All right. So to evaluate logs, what we basically are doing is we're saying that this is equal to x. Okay, so in order to figure out what this log is, I'm going to rewrite it in exponential form. So 4 to the x is equal to 64. So we just need to figure out what power do we raise 4 to in order to make it 64. Well, that would be the third power because 64 is the same thing as 4 to the third. So this is 3. Okay. On B, again, rewrite it in exponential. 8 to the x is equal to 1/64. In order to get that fraction at the bottom, I would need a negative exponent. So I'm going to have to raise this to a negative power, and that negative power is going to be -2. So 8 to the -2nd would be 1/64. Again, the negative exponent is going to move it. Okay. Let's look at C. Rewrite it. 81 to the x is equal to 9. In order to get from 81 to 9, this is probably one of the most missed questions. This very commonly comes up. A lot of people want to say it's -2. We are going to take the square root of 81, but remember, square root as an exponent is not a negative number. A square root is a fraction. So this is going to be the 1/2 power. So this is 1/2. Right? And then finally this last one, 1/3 to the x is equal to 27. So very similar to b, in order to make that fraction a whole number, it needs to flip, it needs to have a negative exponent. So I'm going to raise it to the -3rd power. Okay, the negative will make it just a positive, or sorry, a whole number, not a positive, it already is. So that negative exponent makes it a whole number. 3 to the 3rd gives you 27. All right, so we're going to look at two special bases for logs. So one special base is what we call just the common log, and that is a base of 10. This is the one actually that your calculator kind of will default to. Okay, so just a log without a base written actually has a base of 10. Another one that's going to be very important, especially as you go on in math, is the natural log. So a natural log has a base of e, which we talked about a couple days ago. E is that 2.718 number. So you will never see a log e the way this is written. What that actually is ln, which is a natural log, and that's just the notation. All right, so we're going to evaluate some of these again. So log of 1,000, that's going to be 10 to the x power is equal to 1,000. Well, in order to get 1,000, I would raise it to the 3rd power because there are 3 zeros. Okay, same thing on this one. Let's rewrite it in exponential. 10 to the x is equal to 1 over 100. Okay, in order to move it into the bottom of the fraction, I would need a negative exponent, and then I would have to square it, so it would be -2. Right? Then looking at this one, this is 10 to the x is equal to the cube root of 100. So I'm going to rewrite this. The cube root of 100 is 100 to the 1/3 power. So then this, I'm going to rewrite this as 10 squared to the 1/3 power. So 10 to the x is going to be 10 to the 2/3. So my exponent here then would be 2/3. All right, and then looking at natural log, again, rewrite it in exponential form. Okay, the base here, it's not written, the base is e. So e to the x is equal to e. Well, in order for it to be the same thing, x has to be 1. So the natural log of e is 1. In fact, the way I used to tell my kids to remember this, the word lne, it kind of looks like the word 1, because you just turn that into a little o, and now it says 1. Okay, so the natural log of e is 1. And then the last one, ln of 1. Again, rewrite it in exponential. E to the x is equal to 1. Well, the exponent you would raise anything to for it to equal 1 is going to be 0. Okay, and that property, actually, both of those are down here. We did it for ln on this example, but for any log, if it's the log and the base matches the argument, then it's going to equal 1. Or if you're doing the log of any base of 1, that's going to give you 0. All right, so now we're going to look at how to actually plug these into our calculator. So log base 3 of 7. Now you're going to learn something a little bit later about change of base formula, but for right now, actually, there is a way on our calculators to evaluate these pretty simply. So what we would do is we are going to start on the run matrix screen. Okay, we're going to go to math, and then you're going to see this option that says log AB. Okay, this is the log button you are going to want to use because this allows you to use different bases. Okay, if you choose just the regular log option, okay, that will force you to use a base of 10. So that one will only work if the base is 10. Math and then log AB, that is the option that you want to use. Okay, so we're going to go ahead and use that. So I'm going to do log AB, and then again, that allows me to enter that different base. So this is a base of 3. I'm going to fill in the argument of 7. And now I can figure out that that log is equivalent to 1.771. That means 3 raised to the 1.771 power would give me 7. right? If it's just a natural log, we can just type that in. ln is right by that E button. Okay, so that is right next to log. So the natural log of 4, 1.386. Okay, and that means E raised to the 1.386 power. And again, we can check it if we want to. Okay, E raised to that power gives me 4. Okay, the natural log of 3e. Okay, if I want to evaluate that. So the natural log of 3e. So it forces me to put an exponent, so we're just going to say to the first. All right. And then again, we can round from there, and I should have put some parentheses on that. I apologize, guys, just for good practice. That way we know that this is the argument of our log. All right. And then looking at D, I'm sorry. So in order to do D, I need to rewrite that as a log. This is the one we had in the very beginning of our notes. So this is log base 2 of 6 is equal to x. So to evaluate this, I would type in log base 2 of 6. And in order to do that with a different base, I'm going to do log AB. All right, log base 2 of 6. So I get 2.585. So 2 raised to that power would give me 6. And then the final one, it's a base of 10. So this is a case where if I want to, I can use the regular log. Okay, I'm going to go ahead and rewrite this. This is log base 10, which I don't have to write, of 14 is equal to x. Okay, so again, a base of 10 is just understood. So log of 14, if you typed it in with a base of 10, you'll still get your answer, but this is the case where you could just use regular log. Okay, but when it's base 10 is the only time we want to use the actual log button. All right. So we're going to look at some properties. Because exponents and logs are inverses of each other, you do have some special properties. So one of those properties, these are both based off of composition. So we know that if two functions are inverses, f of g of x is going to equal g of f of x. And those will both equal just regular old x. Well, log base b of b to the x, that is a composition. You've replaced log base b of x. Okay, you have replaced that with b to the x. Okay, the other way around, b to the x, I replaced this with the log function. So if you have expressions that look like these forms, your answer is just going to be whatever that exponent is or whatever that argument is. All right. So this one is one that will make a little bit more sense once you actually see some examples. So I have 8 raised to the log base 8 of 4. So because those 8s match, my answer here is 4. Log base 7 of 7. Because those match, this answer is negative 3x. Okay. E to the natural log of 20. Because the base of this is e, those bases match, that answer is just 20. Okay. The log ones are a little bit easier because if you forget, you can just rewrite it in exponential form. So if I did 7 to the x is equal to 7 to the negative 3x, it's pretty obvious that x is equal to negative 3x. Okay. But it's still good to know those properties just to be able to get this done quickly. All right, so since they are inverses, we're going to go ahead and write some inverses. So what I would do is I would flip my x and y's. Okay, so this would be x equals 11 to the y. And now we know how to rewrite this using logs. Again, because I think it's a little bit easier, I'm going to put what's by itself on the right side. And then I start at my base. I go in a circle. So that is the inverse of that function. Same thing on b. Rewrite it, switch your x and y's. So x equals the natural log of y plus 6. Okay. Again, I'm going to switch it because I just think it's a little easier to write it when what's by itself is on the right. So e to the x is equal to y plus 6. Now again, you don't have to switch it on that step. I just think it's a little easier that we don't get confused. Okay, but if you don't, just remember you would need to go. You need to go in the opposite direction if you didn't rewrite it. So just keep that in mind. All right, so again here, last step would just be to subtract 6. So the inverse would be e to the x minus 6. All right, so the last thing we're going to look at, because these functions are inverses, that means the graphs are going to be inverses of each other. So we've talked a lot about this graph, b to the x. Okay, it's going to go through 0, 1, 1 comma the base, negative 1, 1 over the base, and have an asymptote at y equals 0. Okay, so that graph is going to look something like this. Well, the log graph is the inverse of that. And in inverse, we switch x and y. So this graph is going to go through 1, 0, base comma 1, 1 over the base comma negative 1. And instead of having a horizontal asymptote, this graph is going to have a vertical asymptote. So your log function, again, is going to be dependent on the base, but it's going to have this shape. It's going to go through the base comma 1. All right, domain and range, again, x and y's are flipped, so domain and range are flipped. Domain here was negative infinity to infinity, but range was 0 to infinity. Well, on your log graph, domain is from 0 to infinity, and range is from negative infinity to infinity. All right. And remember we said for if your base was less than 1, the points were the same. It was still 0, 1. It was still 1 comma the base, negative 1, the reciprocal of the base, and y equals 0. But the shape was flipped. Remember, this would show decay instead. Okay. Your log graph is going to do the same thing. Okay. Your graph is actually going to go in that opposite direction, because if you think about it, if your base was, it's going to go through 1, 0, and it's going to go through base comma 1. But that base is going to be something like 1/2. Okay. And then the reciprocal is going to be something like 2. So your graph instead is going to go this direction if that base is between 0 and 1. Domain and range, though, would not change. Domain here, negative infinity to infinity, and range here is 0 to infinity. Domain here is 0 to infinity, and range is negative infinity to infinity. All right, so we're just going to look at an example. We're going to do a lot more with these graphs with transformations next class, but just a basic example to see what it looks like with a certain base. Okay, if it has a base of 2, it's going to go through 1, 0. It's going to go through base comma 1, and it's going to go through 1 over the base, negative 1. And it's going to have a vertical asymptote at x equals 0. So your log graph is going to look like this. All right, again, we're going to do a lot more of these graphs when we do transformations next class, but it's good to at least see the parent functions so you understand the relationship between them. Okay, those two functions are inverses of each other. So this is the inverse of 2 to the x, which had a shape of this. And remember, inverses are reflections over the line y equals x.